Hello, my dear students. This is the part second of lecture fourth. So, in this lecture, we discuss a very important example, which is very important from the major theoretic point of view. So, for this example, actually, we have to show that the function mu, which is defined on the semi-closed interval, is equal to b minus a. We show that this set function is a measure. Here S is the class of semi-closed interval, which is a semiring, which has been already shown, and then we define the set function mu on that class of semi-closed intervals by mu of a. B is equal to b minus a, and we show that this set function is a measure. So in order to prove this, we prove more general result here. That's this example. So here f is a we have f is a function from R to R, be a non-decreasing function. In other words, we can say it's an increasing function which is left continuous. Left continuous means it's left continuous at every point of R. So that means for all a belongs to R, limit x approach to a, f of x equal to f of p. X approach to a means x is approaching from this left to right. It is a left hand limit. That's why we write here x increases to a. X increases to a means x approaches to a and x is less than a. It means we can write it as x increases to a. So x increases to a means that x is approaching to a and x is less than a. So left hand limit means that x approaches to a from the left, and this limit should be equal to the value of the function at that point. So here this f is non-decreasing and it is left continuous at every point. Next, let S be a class of semi-closed intervals. A, B, A, B belongs to R. Then we know that S is a semiring. Now we define a set function on S by, which is very important, by mu of phi equal to 0, and mu of the semi-closed interval AB is equal to f of b minus f of a, which is always greater or equal to 0, because f is an increasing function and b is greater than a. That means f of b is greater or equal to f of a. So therefore the value of this set function lies in the interval 0 to infinity. We show that this set function is a measure on S. So first property, which is trivial, mu of phi is equal to 0. That's by definition we have defined mu in a way that its value on this set phi set is equal to 0. So next property, which is very important, that mu is a sigma additive. So that means we have to choose any disjoint sequence of semi-closed intervals in S such that their union is also a semi-closed interval, and then we need to show that mu of that union is equal to sum of the mu's. So let's prove that sigma additive property of mu. So now we prove the second property that mu is sigma additive. Mu is sigma additive. So for this sigma additive, we choose any disjoint sequence in S, where S is a class of semi-closed intervals. So let's choose let a n b n greater or equal to 1 be a disjoint sequence in S such that the union a and b and n runs from 1 to infinity belongs to S. So and let's take this union is equal to let's write this union as, because it's a member of semi-closed class of semi-closed interval, it must be some semi-closed interval. Let's write it as a b. So what we need to show that we need to show that mu of that union or mu of this interval is equal to sum n runs from 1 to infinity mu of a and b. So we show that mu of union n runs from 1 to infinity a n bn is equal to summation n runs from 1 to infinity mu of a n bn. And now we make the following notation, let S be equal to summation n runs from 1 to infinity mu of a n bn, and by definition of mu it's equal to summation n runs from 1 to infinity f of bn minus f of bn. So let's make this notation. S is equal to that sum. So we show that S is equal to mu of that union. So now for so let k be any positive integer. Is any positive integer, we rearrange the intervals, k semi-cruised intervals, such that a1 less than b1 less or equal to b2 less than a2 less or equal to, and it's here less or equal to ak less than bk. So we can rearrange these intervals. If they are not in this order, we rearrange them. So because here we have these intervals a1 b1 is somewhere here, they are disjoint. a1 b1 a2 b2, a2 b2 is somewhere here, a3 b3 is somewhere here, and a4 b4 it's but at the same time the union of all these intervals is again a semi-closed interval. So here a3 is less than a1, a3 is less than b3, b3 is less than, so we rearrange these intervals. We rename these intervals, or we can rename these intervals. We name this interval a3 b3 as a1 b1 and then a2 b2. So for k greater than or equal to 1, we can rearrange these k intervals like this. a1 less than b1 less or equal to b2 less than a2 and so on up to this is less or equal to ak less than bk. Then we have now this summation I runs from 1 to k, where k is any natural number or any positive integer, f of bi minus f of ai. It's equal to, we can write it as we first expand this sum. It is f of b1 minus f of a1 plus f of b2 minus f of a2 plus the last but 1, it is f of bk minus 1 minus f of ak minus 1 plus f of bk minus f of ak. So let's write it as it's f of f of a2 minus f of a1. Okay. So we can write it as summation I runs from 1 to k minus 1 f of bi minus f of ai plus the last term of this sum, which is f of bk minus f of ak. So we don't need to expand it here. And this bi, what's bi? We have here we have arranged this sequence in a way that B1 is less or equal to A2, B2 is less or equal to A3. In general, Bi is less or equal to Ai plus 1. So that means f of Bi must be less or equal to f of Ai plus 1. F of Bi is less or equal to f of Ai plus 1. So here it's f of Bi, it will be less or equal to, because f is an increasing function, Bi is less or equal to Ai plus 1, so f of Bi is less or equal to f of Ai plus 1. It will be less or equal to summation I runs from 1 to k minus 1 f of A I plus 1 minus f of Ai plus f of Bk minus f of Ak. Now let's expand this sum. It's f of A2 minus f of A1 plus f of A3 minus f of A2 plus the last but 1 k minus 2 f of A k minus 1 minus f of A k minus 2 minus f of A k minus 2 minus f of A k minus 1. It is here minus, then last one, this term, it is f of Bk minus f of Ak. Look at this sum. F of A2 will go with this minus f of A2. These two will go, and at this last, it will be go with this f of Ak minus 1. Okay. It's here f of A1. This is here f of Ak. Sorry, f of Ak minus f of Ak minus 1. This will go with this, and we have here what we remain here. This is f of A1, and then f of A3 will go with the next term, and f of Ak minus 1 will go with this term, and here f of Ak, f of Ak will go with this term. Not it will, how it will go with this term. It's a minus f of Ak. Sorry. For I equal to k minus 1, it's f of Ak. So it's a plus actually, not minus. Sorry, it's plus here. Plus, okay. Now this one plus f of Ak. This will go with minus f of Ak, and it is minus f of Ak minus 2. It will go with the previous term. So there remain only these two terms. One is plus f of Bk and minus f of A1. Plus f of Bk minus f of A1. Now, since it's given that the union of all these intervals is equal to AB, AB is equal to union and runs from 1 to infinity, A and Bn, so it means that this A is less or equal to An, and this Bn is less or equal to B for all n. So in particular, A is less or equal to A1, and this is lesser, Bk is less or equal to B. And function is monotonic and increasing, therefore f of Bk is less or equal to f of B, and f of A is less or equal to f of A1, therefore minus times f of A will be greater or equal to minus times f of A1. Minus f of A1 is less or equal to minus f of A, so it's less or equal to f of B, because f of Bk is less or equal to f of B, and this minus f of A1 here it's actually f of A is less or equal to minus f of is less or equal to f of A1. Now apply the minus on both sides. This gives minus f of A1 will be less or equal to minus f of A. This is true for all k greater or equal to 1. That k. So it's S here. S is less or equal. So it's not S here. This is the summation. I runs from 1 to k of f of Bi minus f of Ai. Letting k approaching to infinity, it gives summation. I runs from 1 to infinity f of Bi minus f of Ai is less or equal to f of b minus f of a, and that's equal to the mu of the union, that's equal to mu of the interval a comma b, which is equal to mu of union n runs from 1 to infinity a n b n. So here I can write it as a b n a n, n runs from 1 to infinity. So that proves the one side of the inequality. Now we prove the reverse inequality. This series some n runs from 1 to infinity, f of bn minus f of an is less or equal to the mu of the union. And we can write this as, this is a summation n runs from 1 to infinity, mu of a and bn is less or equal to mu of union n runs from 1 to infinity a and bn. This is it. To prove the reverse inequality, we use the continuity, left continuity of f. To prove reverse inequality, let delta be any positive number and 0 less than epsilon less than b. We need two positive numbers. Okay. So for all n greater or equal to 1, f is continuous at n. So therefore for all n greater or equal to 1, we can choose Cn such that this Cn is less than a, very close to a. Choose Cn such that for all n f is continuous at a, and therefore for all n greater or equal to 1, choose Cn such that this and we have this mod of f of x minus continuity at a n, left continuity, is less than delta times 2 power 1. This is your epsilon. Whenever the point x is very close to a n, Cn is also close to n, this Cn is less than x and less or equal to a n. This is the left continuity. By left continuity, can write here it is by left continuity at a. Here I should write f is left continuous, not continuous. Left continuous at. So to prove reverse inequality, we use the left continuity. So for this, let choose any delta positive and any epsilon positive. Now for all n greater or equal to 1, f is left continuous at an. Therefore, for all n greater or equal to 1, we can choose Cn such that Cn is very close to an. And whenever the point lies between Cn and an, in other words, that point is very close to an, the difference of their images, f of x and f of a, will be less than delta times 2 power minus n. Okay, let's erase it here. So this can be written as we can remove the modulus. We can write it as f of an minus f of x, because an is greater or equal to x. So we can remove this mod. It's less than 2 power minus n into delta whenever Cn is less than x less or equal to n. So this is a very important expression here. Let's write it as we'll name this expression as a star. We'll use this in future. Now this closed set A comma B minus F is a closed interval, bounded closed interval. It's a subset of A to B, and A to B is equal to union n runs from 1 to infinity. That's initially this closed interval is semi-closed interval is equal to union of these semi-closed intervals which are disjoint. And now this Cn is less or equal to An, therefore C and Bn is bigger than A and Bn. In other words, A and Bn is subset of C and Bn. It's subset of union n runs from 1 to infinity C and Bn. So these are now open intervals. The union of these open intervals contains this closed and bounded interval. In other words, these open intervals forms an open cover for this closed and bounded interval. So therefore, this family Cn comma Bn n greater or equal to 1 is an open cover for A B minus epsilon, and we know that every closed and bounded set is compact, and this set is compact. A to B minus epsilon is compact. Compacting means its every open cover can be reduced to a finite subcover. Therefore, this open cover can also be reduced to a finite subcover. So thus there exists K greater or equal to 1 such that A1, B1, A2, B2 up to AK, BK is an open cover of A to B minus epsilon. Such that A B minus epsilon is covered by these finitely many open sets. This is here C and Bn. This is here. Now again we can assume that A is equal to A1. We can assume that this A1 given at the first interval in this disjoint sequence. So that means we can assume that A is equal to A1. A is equal to A1. So if this B1 is less than B minus epsilon, if it's less than B minus epsilon, so and also this B1 it's greater than A, greater or equal to A, so that implies this B1 it belongs to A comma B minus epsilon, which is subset of union n runs from 1 to K C and B. So it means that this B1 belongs to one of the open interval, and we can assume that without loss of generality we can assume that it belongs to the interval C1 B1. So by rearranging, so we can assume that, but it cannot be first interval because it's in the second. It must be in the second interval. Why it's not in the first interval? For if it is in the first interval C1 B1, then B1 strictly lies between C1 and B1, which is not the case. So it lies in some other interval other than C1 B1, and without loss of generality we can assume that it lies in the second interval. So we can assume that B1 belongs to C2 B2. We can assume that B1 belongs to C2 B2. So this implies C2 is less than B1 less than B2. So now we have B2. Again, if B2 is less than B minus epsilon, then it lies in this interval, and hence it is in the union. So it must be in some interval, say it is in C3 B3. So that cannot be in C1 B1. So again, if B2 is less than B minus epsilon, then B2 belongs to C3 B3, and this gives C3 less than B2 less than, and this process must terminate at certain stage because these intervals C1, B1, C2, they are only finitely many, they are only k intervals. Therefore, this process of assumption B1 less than B1 epsilon, B2 less than B1, it must terminate at certain stage. So let mth stage, suppose let m be the least positive, let m be the least positive integer such that this Cm, sorry not Cm, such that Bm is greater or equal to B minus epsilon. So this implies each Bi's they are less than B minus epsilon, while I is equal to 1, 2, up to m minus 1. Up to m minus 1, it satisfies this inequality, but at a certain stage, the inequality must be reversed. So it must be Bm greater or equal to B minus epsilon. But for those pointers, whenever B I is less than, say B1 is less than B minus epsilon, then C2 less than B1 less than B2, and if B2 is less than B minus epsilon, then C3 is less than B2 less than B3. So this gives this Bi, it lies between Ci plus 1 less than Bi and less than Bi plus 1, less than Bi plus 1. Now let's calculate this sum. We can apply the star here now. We can apply star here now because this is the condition for that. That condition is here. So whenever this is true, then we have the following. So now we can apply the star now. This summation I runs from 1 to m minus 1, because up to m minus 1 this is true. F of ai plus 1 minus f of bi, and each difference is less than 2 power, it's less than summation I runs from 1 to m minus 1, it's delta times 2 power minus I by star, right? Star, and that's again less than summation I runs from 1 to infinity. We can remove this out delta, you can pull it out from this sum. It is 2 power minus I, and that series is equal to 1, it's just delta. So that sum is less than delta. That sum is less than delta. So now we see the reverse inequality. Now S, which is equal to summation I runs from 1 to infinity f of bi minus f of ai, and that's greater or equal to summation I runs from 1 to m, because it is now finite sum and each term is non-negative here, as f is monotonic increasing function. So it's greater or equal to this. And let's expand this sum. It's equal to f of b1 minus f of a1 plus f of b2 minus f of a2 plus f of bm minus 1 minus f of am minus 1 plus f of bm minus f of a. So that now we write it as f of bm. We write f of bm at first. It's equal to f of. We move this f of bm to first place, and then we write here. Then we write minus f of a1. So it is just the rearrangement, and then it's here. Minus times f of a2. It's here minus f of a2 minus times f of a2. Then it's b1 GBN minus f of, so that we can use that previous that less than delta, that previous sum is less than delta. It's f of a2 minus f of b1. You can see it. It's minus f of a2 then plus f of b1. That means it's minus f of a2 minus f of b1. It will be equal to minus f of a2 plus f of b1. And next term I will write it minus. It's s is greater or equal to this. Now next term I will write here f of a3 minus f of b2 plus so on. Then minus, it's here minus, minus, minus. So what's here? Minus f of am, f of am minus f of bm minus 1. F of bm minus 1 is plus f of bm minus 1. Okay. So it's equal to f of bm minus f of a1, and minus term is summation I runs from 1 to m minus 1 f of ai plus 1 minus f of bi. So this s is greater or equal to this. Now this one, this is less than delta, so minus term is, this is greater than minus delta, so it is greater than f of bm minus f of a1 minus delta. But what's this bm? Bm is here greater or equal to b minus 1, b minus epsilon, so it's greater or equal to f of b minus epsilon minus f of a1 is same as a. Already it is assumption. Now this is your s. Okay? S is greater than this. S is greater than this. Okay. Now let's since delta is any positive number, epsilon is any positive number, we can let epsilon approach to 0 and delta approach to 0. Then we apply the left continuity of f at b. So letting epsilon approach to 0 and delta approach to 0, and apply left continuity of f at b. So we get this s is we get s is greater or equal to f of b minus f of a, and that's equal to what's